All right, so hi everyone who's in the meeting right now. So today we're going over the 2016 AIME 1, and the first problem we're going to start from is number 5. And so I'll give you a couple of minutes to try the problem on your own before I go over this. All right. All right, so I'm going to start going over how I did this problem now. Hold on a second. Okay. So let A read for D days. So we're introducing another variable. And then, so on the first day, on reads n pages, while the next day, n plus 1. And on the dth day, she reads n plus d minus 1. And in this sum, there's a total of d copies of n. So part of the sum is d times n. And the other part of the sum is 1 plus 2 plus 3 all the way to plus d minus 1, which is d minus 1. Sorry. D times d minus 1 over 2. And we're given that it's a 374 page book, so this equals 374. And then now we look at the time that she took to read the book. On the first day, she read for t minutes. On the second day, she read for t plus 1. And all the way to, similarly to the end pages, on the final day, she reads for t plus d minus 1 minutes. And we can split this sum in an identical way to the one up here. So it just equals d times d. Okay. D times t plus d times d minus 1 over 2. And we're given that she reads for 319 minutes. So this sum is equal to 319. So now we have these two equations. And we can see that both of them have this same factor of the same partial sum of d times d minus 1 over 2. So we can subtract these equations. And when we do, we get that d times n minus t is equal to 55. And now we know that n and t and d are all integers. And so this means that d is one of 1, 5, 11, or 55. And So we can immediately rule out 1 because we're given that there's at least 2 days here. Because it says on the second day I'll read this many, which implies that there's at least 2 days. And so it has to be one of 5, 11, or 55. But now we know that D is an odd number. And when D is an odd number, D is a factor of D minus 1 times D over 2. And it's because there's no factor of 2 in D, which means that the factor of 2 is in D minus 1 over 2. And so we need that D divides both 374 and 319. And since clearly neither are factors of 5, that tells us that D is 11.
Oh, wait, can you explain that reasoning again? Sorry.
Okay. So since D is an odd number, when you look at the factors of D times D minus 1 over 2, D is an odd number and D minus 1 is an even number. So the factor of 2 cancels out with the D minus 1 term, which means that there's still a D term left over. And so that means that this sum is divisible by D. And so this number and similarly these numbers are all divisible by D. And neither of them is a multiple of 5. So we can rule out 5 and 55, and that just leaves us with D equals 11. Did you get that?
Yeah, thank you.
Okay. And so after this, we can just plug in D equals 11 back into these equations. And so 11 times n plus 55 equals 374. And 11 times t plus 55 equals 319. And then so 11 times n plus t is 374 plus 319 minus 110, which is, and the right hand side is simplifiable to 583. And when you divide out 11 from this, you get that n plus t is equal to 53. And so the final answer is 0.53 because of leading zeros. So are there any other questions?
No, we're good.
Okay. Then I'll move on to the next question. And again, I'll give you a couple of minutes to try this problem on your own before I start going over it. All right, so I'm going to start covering this problem now. So you have triangle ABC, and then you let I be the center of the inscribed circle. And you let the angle bisector of ACB intersect AB at L. So the incenter of a circle is one of the definitions of the incenter of a circle is the intersection of the bisectors of the angles. So the bisector of ACB goes through I. ACB. And then so the line, and then so this is point L. And so the line through C and L intersects the circumscribed circle of ABC at points C and D. So now we draw the circumcircle. And the second intersection is point D. And so now you're given that Li is equal to 2 and LD is equal to 3. And so you want to find the distance of IC. So first of all, we can add the two lines IA and IB to the diagram. Okay. So now these are all angle bisectors, so we can let this be A, this be A, so we can let this be A, this be A, this be B, this is B, this is C, and this is C. So you can also add lines DA and DB. And so when we do this, you can see that angle DCB and angle BAD cover the same arc. So you have that this is also equal to C. And similarly, you have that angle AB is also equal to C. And so that tells you that and so similarly, you can see that CAB and CDB are circumscribed the same arc. So this is equal to this is equal to 2A. And now you can do some more angle tracing here. So this is 180 minus A minus C because it's part of a triangle with angles A and C. And so this is 180 minus this angle, which is 180 minus A minus C. So this is A plus C. And now we can see that triangle DAI is isosceles. And that's because these two angles are both A plus C. And so this ID is 5, and so AD is equal to 5. And similarly, BD is also equal to 5. And so this angle is 2A, and this angle is 2A. And this angle is C, and this angle is C. And these two angles are equal. So you have that triangle CAL is similar to triangle BDL. And so that tells you that BD to LD is equal to CA over AL. And so BD over LD is just 5 to 3. And then now AI is an angle bisector. So by the angle bisector theorem, CI to IL is equal to AC to AL. And we already have here that CA to AL is 5 to 3. And we also know that LI is equal to 2. So CI is equal to 2 times 10 thirds, which is, 2 times 5 over 3, which is 10/3. And so the answer to this question is 0, 1, 3, because you need a leading 0. So does anyone have any questions?
Well, why is BDC 2A again? Angle
Oh,
BDC.
yeah. Okay. So angle BDC circumscribes this arc, and it also and angle CAB also circumscribes the same arc. So you have that the two are equal, and you already know this is 2A. Okay. That autocorrect. Okay, but yeah. So are there any other questions? All right. I guess not. So let's move on to question 7. And then once again, I'll give you a couple of minutes to do the problem. All right, so I'm gonna start going over this problem now. So you're given integers a and b, and you're considering the complex number square root of ab plus 2016 divided by ab plus 100 minus the square root of the absolute value of a plus b divided by ab plus 100 times I. And so you want to find the number of ordered pairs of integers a and b such that this complex number is real. So first of all, we can deal with the case where square root of ab plus 2016 divided by ab plus 100 is real. So in this case, you have that the restriction here is that ab is greater than negative 2016. So is at least. And so in this case, in order for the complex number to be real, you need to have square root of a plus b, absolute value of a plus b, divided by ab plus 100 to equal 0. And in order for this to happen, you need the numerator to be 0, which only happens if a equals negative b. But you can't just directly find all pairs of a and b such that a equals negative b because of the denominator. If the denominator is 0, then this number isn't a real number. And if it's only 0 if, in this case, it's only 0 if a is positive or negative 10 and b is negative or positive 10. And so otherwise, you just have that ab is greater than negative 2016. And so the square root of 2016, the floor of the square root of 2016 is 44. So a can be anything from negative 44, negative 43, all the way to 44, except for negative 10 and 10. Except 10 and negative 10. And so this has a total of 89 possibilities, and 2 of them cannot be included. So this case generates 87 pairs. And in the other case, this case is when square root of ab plus 2016 divided by ab plus 100 is complex. The first case was when this was real. So when this is complex, the only requirement here now is that square root of AB plus 2016 equals the absolute value of A plus B. And this is because you know that this cannot be a complex, this cannot have a real and imaginary part at the same time. Because it's the numerator, the thing that you're taking the square root of is always real. So it can either be real or pure imaginary. So in this case, you have AB plus square root of AB plus 2016 divided by AB plus 100 equals the square root of the absolute value of A plus B divided by AB plus 100. And in this case, the only requirement really is that AB is less than negative 2016. And now you know that AB is less than negative 2016, so these numerators will never actually be equal to 0. And now you can square both sides, and this tells you that AB plus 2016 is equal to the absolute value of A plus B. And now we can split this into more cases. So the first case is if A plus B is greater than 0. And in this case becomes AB minus A minus B equals plus 2016 equals 0. And you can use Simon's favorite factoring trick, and you can factor this into A minus 1 times B minus 1 equals negative 2015. And so you can see that this has 0 solutions. And that's because it's always at least one term is greater than the other. And now the other case is if A plus B is less than 0. Hold on a second. Okay. Is if A plus B is less than 0. Yeah, this is the complex case. Oh, sorry, yeah, negative absolute value of A plus B. This is the complex case. And then so in this case, you have that AB plus A plus B plus 2016 is equal to 0. And then so A plus 1 times B plus 1 equals negative 2015. Actually, sorry. When you combine these two cases, there's a total of 8 each, where A plus A is greater than B or A is less than B. Sorry, there's a total of 1/2 each, not 8 each. And now you can factor negative 2015. And this is negative 1 times 5 times 13 times 31. And so this creates a total of 2 to the 4 equals 16 cases. And 1/2 of the cases go here, and 1/2 of the cases go here. And so this case generates a total of 16 cases. And the first case generates a total of 87 cases. And so the answer is 103. So are there any questions? Okay. So I'm going to move on to the next question now. Alright, so I'll start going over this problem now. So you have a permutation A1, A2, all the way to AN of the digits 1, 2, 3, 4, 5, 6, 7, 8, 9. And so you let SP be the sum of the three-digit numbers A1, A2, A3, A4, A5, A6, and A7, A8, A9. And so you let M be the minimum possible value of S of P, given that the unit digit of S of P is 0. And let N be the number of permutations of P such that S of P equals N. And so you want to find the absolute difference between M and N. So first of all, in order to minimize S of P, the first thing we should do is let A1 plus A4 plus A7 be equal to 1, 2, 1 plus 2 plus 3, or 6. And then now have that A3 plus A6 plus A9 is congruent to 0 mod 10. And you can see that 30 and 0 are both impossible. So this is either 10 or 20. And so we're trying to minimize SFP. So in order to do this, and given that the digits have a fixed sum, in order to do this, we should maximize the sum of the unit digits. And so we let them add up to 20. And now the final digits are A2 plus A5 plus A8. And their sum is 45 minus 20 minus 6, which is 19. And so the minimum possible sum is 6 times 100 plus 19 times 10 plus 20, which is equal to 810. And now we need to find what n is. And so we already know what A1, A4, and A7 are to a factor of 6. And so in order to determine what A3, A6, and A9 are, now we need to do a bit of casework. And so the first case is when the maximum value of all of the numbers is 9. And in this case, the other two numbers add up to 11. And since 1, 2, and 3 are already taken, yeah, that the numbers are 9, 4, and 7, or 9, 5, and 6 in some order. And if the largest number is 8, then the others add up to 12. And the only way to do this without using 1, 2, or 3, and without repeating an 8 or a 6 is 8, 5, and 7. And so now there's 3 ways we can find the digit in here, and 6 ways to arrange those digits into A3, A6, and A9. And the final 3 digits go into A2, A5, and A8. And there's, again, 6 ways to arrange these digits. And so n is equal to 6 times 6 times 3 times 6, which is 648. And so the absolute difference between m and n is 810 minus 648, which is 162. So the answer is 162. Are there any questions?
Nope.
Okay. If not, let's move on to the next question. Alright, so I'll start going over this problem now. So you're given triangle ABC, and you have that AB is equal to 40, and AC is equal to 31. AB is equal to 40. Okay, AB is equal to 40, and AC is equal to 31, and sine of ABC is 1/5. And now you're given that the triangle is inscribed in rectangle AQRS with B on QR and C on RS. And so the rectangle would look like this. And this is Q, R, and S. Okay, this is 40 and this is 31. And so you want to find the maximum possible value of AQRS. So you can let these angles be A and this one be B. And so you have that CS is equal to 31 sine of A, and AS is equal to 31 cosine of A. And similarly, AQ is equal to 40 cosine of B, and BQ is 40 sine of B. And so the area of AQRS is 31 times 40 cosine A times cosine B, or 1240 cosine A cosine B. Okay, and you can use the cosine product to some formula. So that tells you that cosine A cosine B is equal to 1/2 of cosine A plus B plus cosine of A minus B. And so from here you can continue to 620 times cosine of A plus B plus cosine of A minus B. And so cosine of A plus B is also equal to cosine of A plus B equals sine of 90 minus A minus B. And here, sine of 90 minus A minus B is angle A. And in the problem statement, you're given that sine of A is 1/5. So this is equal to 1/5. And now the maximum possible value of cosine of A minus B is 1. And this is achieved when A equals B. And so the maximum possible area is 620 times 1 plus 1/5, which is equal to 744. So the answer is 744. Are there any questions? All right. If not, we'll move on to the next question. All right. So I'll start going over this problem now. So you have a strictly increasing sequence of positive integers a1, a2, a3, so on. And they have the property that for every positive integer k, a2k minus 1, a2k, and a2k plus 1 is geometric, and a2k, a2k plus 1, and a2k plus 2 is arithmetic. And so given that a13 is 2016, find a of 1. so let A1 just be equal to A, and let A2 equal AR. And so then you have that in order, the terms are AR, AR squared, and then 2AR squared minus AR, then 4AR squared minus 4A plus A, and this is AR squared. Well, you can write the factored form on the bottom. So this is A, actually, so this is AR, AR squared, 2AR minus 1 times AR, A times, actually, this is a bit wrong. A times 2, okay, AR times 2A, 2R minus 1, sorry. And this is 2R minus 1 squared times A. And then this term is 6A squared minus 7AR plus 2A. And this factors as 2R minus 1. A times 2R minus 1 times 3R minus 2. And the next term is 9A squared minus, okay, 9A, 6AR squared here. And this is 9AR squared minus 12AR plus 4A. And this factors as 3R minus 2 squared times A. And you can just repeat, and then so the pattern here should be obvious by now. And it holds, so eventually you have that the 13th term is A times 6R minus 5 squared. And this is equal to 2016. And so now you know that A is an integer. And so the only squares that can possibly work for 6R minus 5 are, and 2016 factors as 2 to the 5th times 3 squared times 7. So the only possible squares here are 1, 2, 3, 4, 6, and 12. And so remember that R doesn't necessarily have to be an integer, but all of these terms do need to be integers. And eventually, you can find that the only way that this is an integer is when 6R minus 5 is equal to 2. And then this is because you need to plug them in. And so A is equal to 2016 divided by 2 squared, which is 504. So the answer is 504. Are there any questions? Okay. If not, let's move on to the next question. Alright, so I'm going to go over this problem now. So you have that p of x is a non-zero polynomial, and you have that x minus 1 times p of x plus 1 equals x plus 2 times p of x. And this holds true for every real x. And you're also given that p of 2 squared equals p of 3. And so you want to find p of 7 halves. So first of all, if you plug in x equals -2 into here, you have that -3 p of -1 equals 0. And so p of -1 equals 0. Then you can plug in x equals -1 into here. And so -2 p of 0 equals 0. So p of 0 equals 0. And now you can plug x equals 0 into here. And so you have that -p of 1 is equal to 0. So p of 1 is equal to 0. And when you plug x equals 1 into here, you just get 0 equals 0. So now you can let p of x be q of x times x plus 1 times x minus 1. And now you can plug this into here again. And when you do that, you get that q of x plus 1 times x plus 2 times x plus 1 times x minus 1 equals x plus 2 times q of x times x plus 1 times x minus 1. And all of these terms cancel out, and you're just left with q of x minus 1, x plus 1 equals q of x. And so that tells you that q of x is a constant polynomial, so it equals a for some real a. And so now we look at p of 2 squared equals p of 3. If we plug in x equals 2 into this equation, if you plug in x equals 2 into this equation, you get that 4 times p of 2 equals 1 times p of 3. And when you compare these two equations, you can quickly see that p of 2 must be equal to 4. And that's because you clearly can't have that. This is equal to 0 for p when x equals 2, unless you have that q of x equals 0, but you're given that it's a non-zero polynomial. So p of 2 equals 4. And so when this is true, so now you have that a times 2 plus 1 times 2 minus 1 is equal to p of 2, which is 4. And so this is 3 times 2 times 1, which is 6. So a is 2/3. And so now so now you have that p of x equals 2/3 of x plus 1, x times x minus 1, which is 2/3 times. And so you want to find p of 7/2. Okay. And so p of 7/2 equals 2/3 times 9/2 times 7/2 times 5/2, and 9 times 2/3 is 6, and 6 times divided by 2 is 3, and so this is 105 divided by 4. And so the final answer is 105 plus 4, or 109.
Wait,
So okay, what?
Can you explain why p of 2 equals 4?
Okay. So you can plug in x equals 2 into this equation. And when you do that, you get 1 times p of 3 is equal to 4 times p of 2. And so you're also given that p of 2 squared equals p of 3. And now you can divide these equations because you're guaranteed that p of 3 is not equal to 0. Because if it were equal to 0, if you plug in x equals 3 into here, you get that this is 24 q of x, and the only way this is equal to 0 is if q of x is equal to 0. And the only way but you're given that p of x is a non-zero polynomial. So q of x cannot be 0. So p of 3 cannot be 0. And so you can divide these equations, and when you do it, you get that 1 equals 1/4 p of 2, or p of 2 equals 4. So does that answer your question?
Yes.
All right. Are there any more questions? Okay. If not, let's move on to the next question. Right. So I'll start going over this problem now. So you're trying to find the least positive integer m such that m squared minus m plus 11 is the product of at least 4 not necessarily distinct primes. And so, first of all, we can factor m squared minus m plus 11 into m times m minus 1 plus 11. And so, this term is always even, so m squared minus m plus 11 is always odd. And so that means that you can safely multiply this by 4. So let p be a prime divisor of m squared minus m plus 11. And it's just p because it's prime. And so we've now established that p cannot be equal to 2. So this means that p also divides 4m squared minus 4m plus 44. And so this is also equal to 2m minus 1 squared, 2m minus 1 squared plus 43. And so if we turn this into modular arithmetic, it just means that this is congruent to 0 mod p. And so this means that 2m minus 1 squared is congruent to negative 43 mod p. And so now we can look at when p equals 3. And when p equals 3, negative 43 is congruent to 2 mod 3. And so this is bad because 2 is not a quadratic residue mod 3. And when p is equal to 5, negative 43 is congruent to 2 mod 5. And all squares mod 5 are either the form 0, 1, or 4. And so this is bad as well. And when p equals 7, you have that negative 43 is congruent to negative 1 or 6 mod 7. And in mod 7, perfect squares can either be 0, 1, 2, or 4. And neither of these is 6, so this case also fails. So p must be at least 11. And if you test 11, negative 43 is congruent to 1 mod 11, which is clearly a quadratic residue. And so the smallest possible value that we can have for m squared, the smallest possible value we can have for m squared minus m plus 11 is m squared minus m plus 11 is equal to 11 to the 4th. And that's because we've now shown that 11 is the smallest possible prime divisor, and it says at least 4 not necessarily distinct prime. And so in this case, we have that 4m squared minus 4m plus 44 is equal to 4 times 11 to the 4. Or 2m minus 1 squared equals 4 times 11 to the 4th minus 43. And so clearly this is less than 4 times 11 to the 4th, which is also equal to 2 times 11 squared squared. However, the difference between 2 times 11 squared squared minus the perfect square smaller than it, which is 2 times 11 squared minus 1 squared, is greater than 2 times 11 squared, which is greater than 43. But the difference in here is 43, which means that this is a number between two consecutive perfect squares. And so this case does not work because m is not an integer in this case. And so the next smallest case after this is when we increase one of these factors of 11 by 1. And when we do this, we have m squared minus m plus 11 is equal to 11 cubed times 12. Hold on a second. Okay, sorry. And so in this case, we have that m squared minus m is equal to 11 times 11 squared times 12 minus 1. And so you can manually multiply this out. Sorry. I wrote the wrong number here. And this is 11 cubed times 13 because it has to be prime. And so this is 11 times 11 squared times 13 minus 1. And so you can multiply out 121 times 13. And this is 363 plus 1,210 or 1,573. Okay. And then so this is 11 times 1,572. And when you factor it, you get that this is 2 squared times 3 times 11 times 131. And we can recognize this as 132. And so this means that if we let m equal 132, then we have that m squared minus m plus 11 is equal to 11 to the 4th, 11 cubed times 13. And since we just wanted to find the smallest positive integer m, such that this is the product of at least 4 non-necessarily distinct primes, then we have that the answer is just 132. So does anyone have any questions about this problem?
So why was the 11 to the 4th not valid? Like, what was the reasoning that led to the conclusion that it was not valid?
So here, m squared minus 11 plus 11 equals 11 to the 4th. And then so we multiplied both sides by 4. And then we subtracted 43 from both sides. And so 2m minus 1 squared is equal to 4 times 11 to the 4th minus 43. And so clearly this is smaller than 4 times 11 to the 4th, which is equal to 2 times 242 squared. And now 242 squared minus 241 squared is 400 something. But this is 43, which is a lot less than 400 something. And so that means that this is still greater than 241 squared. And this is a number that's between two consecutive perfect squares, but it should have been equal to a perfect square itself in order for 2m minus 1 squared to work. And so that's why it didn't work. Did you understand that?
No, can you explain that last part a bit? Sorry.
Okay. So
Sorry.
Okay, it's fine. So basically, 241 squared is 242 minus 1 squared, which is 242 squared minus 484 plus 1, which is 4 times 11 to the 4th minus 483. So then we have that 4 times 11 to the 4th minus 43, which we said was equal to 2m minus 1 squared, is between 241 squared and 242 squared. But this was supposed to be a perfect square, but it's confined between two perfect squares,
Okay, that makes
and
sense.
both with strict inequalities.
Okay.
So do you get it now?
Yeah. Okay, thank you.
All right. So I guess that was the final problem for today. And please try to do more of the homework on time. And so bye, and I guess you can leave now if you want.